Good morning. My name is Ron Lewis, and I'll be doing the presentation today. First, I'd like to thank everyone for taking time out of their schedule to attend. Today, we'll be talking about introducing the CombiFlash Rf plus pure ion flash mass spectrometry system. As you've seen, we've sent a note out that says that if you have questions, simply enter those in the chat screen. To get to the chat screen, you should have at the top of your screen a little thing that says you are viewing Ron Lewis's applications. If you click on that tab, there's a drop that'll drop down, and there'll be a box there that you can check for chat so that you can get to the chat window to type in your question. The CombiFlash Rf plus pure ion system is a fully integrated flash chromatography mass spectrometer system. And the real purpose is to provide mass-directed purification and compound verification during the flash separation. Some of the topics we're going to cover today is why flash mass, how it works, some of the user controls that the user has access to, an example of some of the user interfaces that the user would interface, and then some applications showing the applicability and what you gain from flash mass. One of the most common questions is why flash mass? Flash chromatography is a very simple technique. It's quick, and many times mass spectrometry is interpreted as being very complex and more research-oriented, and so it doesn't make sense on the surface to marry the two together. But the real reason to do it is to connect the two is, one, to find out the molecular weight of the compound that's eluting out of the column, to possibly gain some information into structure of the compound as it elutes from the column. It provides the ultimate in selectivity. If you're an organic synthesis chemist, you have a target compound that you're trying to synthesize. You know what the mass of that compound is going to be. And by using a mass spectrometer as the detector, you can simply program the mass spectrometer to collect only that mass and everything else be shunted to waste. It gives you visibility of co-eluting contaminants. In other words, if the mass changes during a peak, you'll see that, and that change could trigger the fraction collector to advance to another tube. The most time-saving thing is probably mass confirmation of collected fractions to avoid offline TLCs or post-purification workups and core lab LC mass spec analysis. Often today, customers run their samples, they collect the fractions, and then they either run a TLC plate to verify where their compound of interest, what tubes their compound of interest is in, or they go through a workup, place an aliquot out of each tube into an autosampler vial, take it down to a central open access or core lab LC mass spec, run a quick HPLC trace with mass spectral information to determine where their compound of interest is located. By putting the mass spec in line with the flash, all of that post-purification work is eliminated. Just a quick overview of how mass spec compares to other flash detectors. Most common is obviously UV detectors. UV detectors gives a nice linear response. Not all compounds can be detected because it has to have some single double bond conjugation to absorb in the UV. the user has to really have an understanding of where his compound has UV absorbance at what wavelength, so that the correct wavelength is selected to monitor and collect. And it's not selective. Anything that has a UV response will respond. Now, many people have moved to putting an evaporative light scattering detector, or ELSD, in series with the UV detector. It's more universal than UV because it measures light that's scattered from any semi-volatile and non-volatile particles that have been dried out of the mobile phase through evaporation in the evaporative light scattering detector. It's still not selective because anything that is semi-volatile or non-volatile will scatter the laser light at the detector in the ELSD and give a response. The mass spectrometry, on the other hand, covers a broad range of organic compounds, but it is not a universal detector. But it provides some chromatographic data as it identifies the compound by confirming its mass. And based on some simple fragmentation, you can oftentimes see the loss of an amine group, chlorine, bromine, that are easy leaving groups that can be cleaved off during the ionization process. So you verify your target ion, as also you can glean some information into compound structure. And this just kind of summarizes what the benefit to the users are. First, you can determine the presence of co-eluting impurity. Oftentimes, if you look at a UV peak, compounds either are totally co-elute or partially co-elute to where you have maybe a shoulder in the front or the back. You can quickly see that with a mass spectrometry where the target ion changes as you go through the peak. By using the mass spectrometer as the driver for the fraction collector, the mass spectrometer can actually advance to another fraction vial and collect that impurity separately from the peak of interest. Secondly, we talked about this a few minutes ago, collecting only on the target mass. What that does is it increases throughput. One thing that is an option in the pure ion is to terminate the purification after the target mass has eluted. In other words, if I have a target mass of 195 and I set the system up to terminate after the target is eluted, as soon as the peak from the mass generated by the mass spec returns to baseline, it terminates the run, lowers your solvent consumptions, and increases your throughput by decreasing runtime. Secondly, we talked just about this just a minute ago, is eliminating the need for post-purification analysis. Another thing is if you're doing natural products research, you can program the system to collect over a mass range. So if you're interested in higher molecular weight alkaloids or other compounds, you can eliminate some of the lower masses by shunting those to waste and collecting over a mass range of, let's say, 300 to 500 Dalton. So collecting over a mass range is very useful for natural product chemists. Collecting on a target mass is very useful for an organic synthesis chemist. There's four major components that make up the CombiFlash Pure Ion system. You can see over here on the right-hand side of the slide, you can see the CombiFlash Rf+. Obviously, this larger unit here is the Pure Ion detector module. Over here on the left-hand side, you can see the fluid interface. And what's not shown here is a roughing pump. And we'll talk about the use of those products why we use a roughing pump in a moment. First of all, let's just look at what happens in the fluid interface. This is a simplified flow diagram of what goes on in the fluid interface. The purpose of the fluid interface is to take the aliquot from the flow stream from the RF, send it through a splitter valve, and return it back to the RF and to the UV detector. On the other side of this splitter valve is a carrier pump, a pulse damper, pressure transducer to monitor pressure in the line, and then a short sample aliquot that is switched from the RF flow stream into the Mass Spec carrier pump flow stream, and the sample sent to the Mass Spec and ionized and pulled into the Mass Spec from the probe. The RF Plus, the new introduction as well. The RF Plus has the ability to spectrally display the UV spectra in both real-time and post-run. It allows for binary gradients between any two of the four solvents, and a third solvent can be programmed as a constant % modifier. So if the user wants to run a water acetonitrile gradient with a small percentage of formic acid, the formic acid doesn't have to be mixed into the water and the acetonitrile. It can be added from a third reservoir. Like the previous products in the CombiFlash Rf line, it is fitted with RFID sensing on both columns and the collection racks, so that simplified operation. Flow rates up to 200 mils per minute with pressures up to 200 psi, and active solvent and waste management monitoring. One of the things that during the design phase, as we talked to users of flash systems, was they wanted to make sure that the system was simple to operate. And so that was one of our design goals. And so to accomplish that, we embedded single point control of the mass spectrometer into PeakTrak. So it's programmed very similar to UV detectors. Some of the mass spec options that the user can select from is they can select, as we mentioned earlier, between target mass or mass range detection. Has a large mass range, one of the largest mass ranges on the market today, 50 to 1200 Dalton. User can select between positive or negative ionization. The detector comes standard with ESI or electrospray ionization probe. The option to add APCI or atmospheric pressure chemical ionization probe is also available. And that's the reason that we use an external roughing pump. APCI requires a higher flow of nitrogen gas to carry the sample from the probe into the mass spectrometer. And by using the roughing pump, we're able to displace the amount of nitrogen that's pulled into the mass spec. And another option is a pre-purification confirmation. And we'll show you an example of that momentarily. We've simplified flash mass down to a simple three-step process. The first step is to verify that the compound of interest generates a detectable ion. Mass spectrometry specialists will tell you that about 70% of all organic compounds are ionizable and detectable by mass spec. Obviously, this includes the various hydrocarbons, which are not ionizable, and therefore cannot be detected by mass spec. Typically, the ion that's generated is an M+1, and the reason for this small fragmentation is due to the softness, if you will, of the ionization that happens in the electrospray interface. You can also form an adduct. By this, I mean that the ion, the M+1 ion that's formed, may actually add something like methanol, it may add sodium to the mass, and so what you're detecting is an M+1 plus methanol or M+1 plus sodium. And so that's why we want to do the verification of the compound prior to purification, so that we know that we have the target compound, we know that the target compound ionizes, and if it does form an adduct, we want to probably monitor that adduct in addition to the M+1 value. Second step in the process is to simply load the sample. Third process is to press play, and you can select or you can verify your MS target or targets in your startup screen. It's not necessary to go over into Method Editor and build a method to include all your values. You can simply do it in this 3 steps. This is an example of step 1 method development screen. The first thing to do is, as we mentioned, to verify ionization and visible ions. And you can see here that there's a mass spectra trace. It's between, and this one happens to be between 100 and 300 Dalton. And I can select up to 4 target masses, individual target masses, or I can select 3 target masses and a mass range. And those are automatically loaded into the purification method. To select those target masses, I simply display my spectra, and by using a pointer, I can simply select, in this case, maybe 180, 185, and you can see that that's displayed up here in this target mass window. I can use this window to optimize my carrier solvent. We normally run a carrier solvent that we use in the lab of methanol with 0.1% formic acid. However, some users like to use acetonitrile as the carrier fluid. Some people like to use trifluoroacetic acid or TFA as the modifier. And so those changes can be made, and this is simply an injection through a manual injector. The flash system is not running at all. It's just simply controlling this, and this screen is displayed in PeakTrak. So your carrier solvent can be changed and evaluated. I mentioned earlier that you could select between positive and negative ionization. You can make that change here on the screen and re-inject the sample to see how that affects the results. And you can determine the best probe. So simply by going into this screen, you can try the ESI probe. If you don't see your target ion, then you might want to try APCI. Simply a 5-minute switch over to change the probes. Come back into the method development screen and re-inject your sample. Down below here, you'll see where we have this fluid interface pressure. What we're doing is we're monitoring the pressure of the line between the splitter valve and the probe itself, because we want to A, make sure that the carrier pump is pumping properly, and B, this is also an indicator that once the pressure gets up close to this red line that you see here, there could be a clog forming in the system, and that you would clean the lines prior to doing your purification to avoid stopping the system in the midst of your purification. Let me back up 1 second here. You can see up here a button called Target Ion Table. If for some reason you don't see your M+1 displayed in the Mass Spectra window, you can simply click on this Target Ion Table, and you get a display that looks somewhat like this, where you've got your detected mass displayed here. And then we're looking at potential target ions. And so in other words, if 180 would happen to form an adduct with sodium, then the M+1 of that compound would actually be 157. So if your M+1 doesn't show up as a detected mass on the left-hand side in the column on the left, then you can scan through this, and this is some common adducts that are formed. Picks up sodium, picks up potassium, picks up methanol. A lot of compounds will lose water during the ionization process and rearrange to a more stable compound, because every time you ionize, there's an attempt to reach a stable mass, and so some compounds will cleave off H2O. And so if I detected 180, but my compound is possibly rearranged to lose water, then my M+1 with the water would be 198. So upon looking at this table, if I see a compound or a mass that corresponds over here to mass of my target compound, I can simply click this radio button, and that will add that target mass down below here. Likewise, if I don't see my target mass or I want to put in a mass range, I simply click on the keyboard button here, and it brings up my keyboard, my number pad, so that I can enter a target mass range. Once I click OK and close this screen out, and then close the method development screen, all of those values are automatically loaded into the system, and it's ready to run. So I mentioned step 2, simply load the sample. You can do this as shown here with a liquid load, or you can use a solid load cartridge, whichever your preference is. And the final step is simply to press the play button down below. What you see here is you see the gradient conditions. You also see right here listed the M/Z for the mass spec. You see the value of, in this example, 180 to 200 is blue, 180 is teal, 168 is a light blue, and 185 is a darker blue. In the meantime, we're also monitoring wavelength 1 is at 214, wavelength 2 is 254, and this simply indicates that the mass spec has a program, that program values are displayed in this area of the screen. And in this case, we're running a gradient between water and methanol at 30 mils a minute with a 15.5 gram gold column. So by simply clicking play, starts the run, and I begin to acquire data. In this example, you can see that the trace goes on, and this peak corresponds to an M/Z of 170 to 190 in this example. And you can see this is the mass spectral information in real time. And you can see that there's this solid 180 peak. In this example, the M/Z 180 that was being monitored here actually perfectly overlays with this, because this is the primary mass that's being detected. if there was another major mass other than 180 that was being detected here, you would see the teal line lower than the sum of the mass range that's been selected here. And the gray line, 185, is this flat line right in this region because there is no 185 being detected at this point in time. So this is looking at live data. If I wanted to go back and review data prior to this, if I simply click on this screen while I'm acquiring data, it will go back and I can see the mass spectral information at some point in the past, and simply clicking live data again brings me back to the real-time display. And you can see here that this is an example where we've clicked back here, and you can see where this is a fairly noisy value where there's a lot of impurities that are eluting because we're essentially looking at the baseline at this point. Once the run's completed, I have the option of displaying the data, and we've improved on our post-run report so that you have several options. At this point, when you display the mass spec, first of all, you can format the graph to cover whatever region you want. And you'll see down below here, there's M over Z at 6.5 minutes, M over Z at tube A5, M over Z at 8.9 minutes, and M over Z at 11.9. These are 4 spectra that are available, and they will print out this spectra as part of the PDF when I save the PDF file. The one that's highlighted here is M over Z at tube A5. To get that, what I've done is I've simply clicked on the tube over here on the left. You can see that it's grayed in this area here. And what you see is the mass spectra. We've added all of the mass spectras that we took during this time slice, added those together, and give you a relative intensity of the mass spectral information that's contained in that tube. So if we started to see an impurity form, we'd start to see that impurity down here in the mass spectra data. And so therefore we could know that, let's say, tube A5 and A6, which would be this area, we could decide if we wanted to put those together or evaporate those down and keep them separate, because one might have a contaminant that's not in the other. Now you see that in this case there's these extraneous small peaks here. Some of these are just simply impurities that come from the solvents, and there's a variety of sources. Obviously, mass spec is a very sensitive technique, and so it's not uncommon to see those. We identify and label the 10 strongest peaks in the time window. You might ask, what if I don't see the information here that I'm looking for? Well, you can simply format this graph, and you can change the settings on this. This happens to be 100 to 200. I can change this up to 50 to 1200, because even though the data is displayed here, the entire spectral information is stored from 50 to 1200 Dalton. So let's talk a little bit about example applications. What this is an elution of a single compound. What I wanted to do in this example was I wanted to collect thiophthalate, and if you look at this green line here is the mass spectra of thiophthalate. It has a mass spectra of 181, and then it picks up an adduct in this case. So the M+1 is 181. It adds methanol to give you this 213. And so this is typically one of the things you'll see. And here is the mass spectra of caffeine at 195. So what this trace is, this shows me that I programmed the system to collect only the mass spectra at 181, that's this peak, and this peak eluted out, and you can see from the fraction collector down below, it changed when the UV started to see this second peak, even though the mass spec didn't see this new target ion or mass ion present. So the two working in tandem allowed me to collect only the 181 peak and cut out this impurity that had a UV that I was not interested in. And so you can see where we'll have a fairly pure fraction here of my thiophthalene, while the caffeine has been cut out. On the other hand, if I do a mass range collection from 180 to 200 Dalton, you'll see that I have the two peaks here, and you can see the green lines in this particular case, and you'll see that the first peak and the second peak are separated and both peaks are collected. And so between the UV and the mass spec, you're able to separate this into the two components, and we're collecting over a mass range. Another example, this is a good example of a organic synthesis run, whereas we are looking at this, and this is our desired compound that we wanted to synthesize. However, this is the desired compound, benzidine, and this is a potential side product. And as you can see at the mass spec, we got a very nice strong signal here, a somewhat weaker ionization signal here. But it was very easy and quick to find the compound of interest and separate that out, in this case the green band, from a oxidation product that was not my peak of interest. Now if you look at the UV trace, you'll see that the oxidation product looks to be my largest peak compared to the second UV peak. So I might have, if I was just looking at UV, I might well have collected this and said, oh, that's my product of interest that I wanted. And only after doing post-run analysis, TLC or HPLC mass spec, I would have determined that this is not my compound. And so if I hadn't have continued the chromatographic run and collected this second peak, it would have been, my desired compound would have been lost. This is a natural products application where what we're looking at here is a broad spectrum, and you can't really see this. There's a poster on our website where this is much better displayed, but you can see where we've captured several different mass spec peaks here that we've collected, and by looking at the M+1 ion that is being displayed down below and some of the fragmentation that you see here, some compounds could be identified as known compounds. Allows the natural products person to focus on compounds that have exhibiting mass ions that are novel and not commonly known compounds. We've talked about mass spectra. One of the other things to discuss briefly is that what you can do for mass spectra on the RF plus, you can also do for UV, where you can get the UV spectra at any point in time, and that can be displayed in a window underneath. This is both, this example is a post-run UV spectra, but that can also be done in real time as well. Finally, just to go over the RF Plus family, products that we have that can be used commonly in the purification is the RF-150, the RF Plus, which is a UV-based system, the RF Plus Lumen, which is a UV evaporative light scattering detector, the RF Plus Pure Ion, which is the Mass Spec system. It can be combined with UV-Vis, and as well as ELSD. So if you want the ultimate in detection, you can use UV-Vis, ELSD, and Pure Ion all simultaneously. Obviously, we have the RF Torrent for large-scale work, as well as ReadySep and ReadySep Gold columns, a line of fraction collectors, and the last product is our standalone ELSD detector. All of our modules are compatible with the iPad Touch, iPhone, and iPod. And the last thing is, I want to remind everyone of the availability of our flash guide, which can be downloaded from our website, or you can order a hard copy simply by going to isco.com/flashguide, and a free copy will be sent to you. We have a variety of upcoming Flash webinar topics. We're going to be discussing reversed phase in Flash, purification by compound classes, alternative media to silica, a basic introduction to Flash chromatography, and a webinar on the sample loading techniques for consideration of best methods for loading samples and things to watch out for. That concludes the seminar.